All right, let's get started. So before we ensure with our actual topic of the course, which is ship dynamic positioning, and which is going to deal more with guidance, control, and navigation, we need to spend a little bit of an effort to get the convention right for the equations of motion, derive them a little bit, and then be able to understand what are the different frames of references we are using. So we'll spend some time to discuss about the reference frames and then discuss about the equations of motion that we are looking at. And this should take us maybe 1 or at max 2 weeks, and then we should move into guidance and control. So let's get started with that aspect in mind. So we'll define a few reference frames today and try to understand what is the transformation between one frame to the other. Okay, feel free to stop me whenever you are unable to understand something or you have a question, because I'm going to be on my PDF. I'll not be able to see a raised hand also. So please unmute yourself and speak so that I get to know that you have a question. Is that okay with everyone?
Yes, sir.
All right.
Yes, sir.
Okay, so let's get started. Okay, so we will define a few reference frames today. So the first, we will define some frames which are Earth-centered reference frames, which means the origin point of these reference frames is located at the center of the Earth. Now you might wonder, why is this important? Why can't we use a flat Earth coordinate system? And the reason is that these are particularly important when we are looking at something called terrestrial navigation, which means when we are looking at satellites or ships which are drifting over large distances, it will be important to start taking these into account. But for a general navigation purpose, a flat Earth coordinate system is good enough. But in order to maintain a consistency, we'll start off with Earth-centered reference frames and make our way into our flat Earth coordinate systems that we are generally used to. Okay. So the first reference frame, we'll call it Earth-centered inertial frame. Okay, and that's what you have the name ECI, Earth-centered inertial frame. And we'll reference this frame or denote this frame by these curly brackets and inside it with I. Okay, this is an inertial frame, as you understand, right? Which means that it is a non-accelerating frame of reference, and this means that the Newton's laws apply in this particular frame of reference. Now, one might really argue, is really Earth a reference frame which is not accelerating because we are going around the sun and the sun itself is going around some other place? But for most practical applications where we are looking at, these accelerations are small enough that we can disregard them, and the Newton's law are well applied, very well applied in the Earth-centered inertial frame. And we'll see more of this come into the picture when we are looking at inertial navigation systems, especially over long ranges. So suppose you are looking at missiles or satellites or things like that, where the distances are really larger than 10 to 15 kilometers, you must need an inertial navigation frame. And that's where these Earth-centered inertial frames will become important. Notice that the X, Y, and Z axis of these inertial frame are represented by X superscript I, Y superscript I, and Z superscript I. The origin OI will be at the center of the Earth in this particular case. And again, this is primarily used for designing inertial navigation systems and terrestrial navigation. All right, now we define a second coordinate system, and we'll call this one Earth-centered, Earth-fixed coordinate frame. Okay, what this means is that it is slightly different from the Earth-centered inertial frame in the sense that now the Earth is revolving around its own axis, and this Earth-centered, Earth-fixed frame or ECEF frame also rotates along with the Earth. Okay, is everybody clear with that?
So in the first frame, the inertial frame, the Earth will be spinning as well. So like with respect to the coordinate frame, the Earth will be spinning, right? But in this case, the Earth
Correct.
would be appearing to be still in the
Correct.
Earth fixed frame.
Yeah, with respect to the Earth fixed frame, you expect to see the Earth to be fixed. So, which means that if the x-axis is going through, let's say, the Greenwich meridian, okay, or this is the zero longitude, then that zero longitude will continue to be going around as the Earth frame is rotating. As the Earth is rotating, so will the coordinate system also rotate. So basically, this coordinate frame is rotating with some angular velocity, which is denoted here by omega IE. Okay, so this is the omega of frame E with respect to I.
Okay.
All right. And now this frame we will call it as frame E. So curly braces E, that is how I'll denote this frame. And the X, Y, and Z axis of this frame are denoted by X superscript E, Y superscript E, Z superscript E. Notice that the origin OE again is at the center of the Earth. So OE and OI are at the same location. Now, since this thing is rotating over time, at any particular time that I look at, I'll find that the XE, YE axis is rotated with respect to the XI, YI axis frame. And that angle it makes is omega IE times T, depending on how much time has elapsed. Okay? Everybody with me so far? So the rotation is occurring about the Z axis.
Yes, sir.
All right. Okay. So here there is some convention. We assume that the XE axis, which is corresponding to the x-axis of the Earth-centered Earth fixed frame, points to the zero or prime meridian and lies in the equatorial plane. So it lies on the equatorial plane and is pointing to the zero longitude. Or this is the place where the Greenwich laboratory is located. The YE axis lies in the equatorial plane and completes the right-hand coordinate frame. And the Z-axis points along the Earth's rotational axis about which the rotation is happening. Okay, so given that XE and ZE are fixed, the YE follows the right-hand rule. That's what it's saying in essence. And if you look at what is this value of the Earth's rotation, you can compute it as 2.7921 into 10 to the power minus 5 radians per second. So this is nothing but which will result in a one rotation in 24 hours. Notice that this quantity here, if I want to represent it as a vector, then I can represent it in either the Earth frame or in the inertial frame. So here what I'm doing is I'm expressing that vector omega IE in Earth frame, in the E frame. Okay, so the same vector when expressed in I frame, I'll replace this superscript E by I. That is the convention that we are going to follow throughout this course. Is that making sense?
Yes, sir.
Okay. Also note that I'll interchangeably use this vector notation and the curly braces, which means that I'm actually putting it as a vector of three quantities. I'll interchange between these two notations fairly often. They both mean the same things, but only thing is that one is talking about a matrix vector, which can be used in matrix multiplications, whereas this one is denoting a regular vector that we are used to seeing in the vector fields. All right, let's come down. Now, ECEF, the Earth-centered Earth-fixed frame, is also used for global navigation applications. This is primarily used for satellites when you're looking at geostationary satellites or polar satellites. It really is important to take into account the rotation of the Earth as well, especially for the geosynchronous satellites, because their rotation rate must exactly equal this rotation rate, which is specified as 7.2921 10 power minus 5. Only then the satellite is in a stationary orbit or a geostationary orbit. All right. So that looked at some of the Earth reference frames. Now we'll formulate some more reference frames, and these we will call as geographic reference frames. And in essence, what these are nothing but they're tangent planes. So if you look at the surface of the Earth and you take a tangent plane to the surface of the Earth, then that is where we are defining these geographic reference frames. So let me go back to the picture here, and you can see here that NED, which is represented here, is one such plane where the XY plane of the system is a tangent to the surface of the Earth. So if you imagine the Earth to be a sort of an ellipsoid, it's not a perfect sphere, so that is why an ellipsoid. Then you will see that if I construct a plane which is normal to the surface here, then it will look something like that. Try drawing it. And this plane is basically tangent at the origin point to the Earth's surface. Okay? Everybody with me so far?
Yes, sir.
So how is the north of that chosen? That ellipse on the ellipsoid tangent plane?
Correct. I'm coming to that. So what we do here is the X is chosen in the north direction. The Z is chosen in the down direction. And then obviously Y will be in the east direction. And that is why you have this name NED. North, east, and down. Okay, so this is the x-axis, this is the y-axis, and this is the z-axis. One could have chosen it in a slightly different way also, and you will kind of see that come up in some of the other studies where they use something called ENU. Okay, and that is east, north, and up. You will also see that convention being a popular convention, but for our purposes, we will restrict ourselves to NED. Okay, north, east, down. So where the x-axis, xy plane lies on the tangent plane to the ellipsoid, with z-axis pointing normally inward towards the center of the Earth, and x-axis lies towards the north direction and y-axis towards the east direction. Okay?
Yes, sir. Yes, sir.
All right. All right, and these sort of geographical reference frames are used for local and terrestrial applications, which means that when we want to look at how a craft moves or how a ship moves between small regions of space, these are the coordinate frames which we'll be looking at. Again, when I'm talking about terrestrial applications, I mean that these are long distances. So they are really long distances that the curvature of the Earth starts to make a difference. And that is why here what happens is you have to take it the longitude and latitude of the craft as it moves across the surface of the Earth. Whereas when we are talking about local navigation, we are really looking at a small geographical area around a fixed value of a longitude and latitude. And in that case, we are only interested in what is called as local navigation, and the curvature of the Earth really doesn't make that big of a difference when we are in and around this longitude and latitude. If we go very far away, then we need to start considering as L and mu are moving. Whereas when you are closer to the point or your navigation is restricted to a certain space, which is locally close to a certain longitude and a latitude, which here I'm calling as L0 and mu 0, then I can get away with what is called as a local navigation frame. And here, this local navigation frame is also known as the flat Earth navigation system. And this is what we generally see, whether it was your maneuvering course or whether it was your ship motions course. When we are defining an inertial frame of reference, we were primarily looking at the flat Earth navigation system, where the the Z was either pointing up or was pointing down into the Earth. This sort of an approximation, where I'm computing a tangent plane at a fixed latitude and longitude, is valid when I am somewhere about plus minus 10 kilometers of area centered around this latitude and longitude. So if I have a area which is about 10 by 10, 10 kilometers by 10 kilometers, so then I'm somewhere here, then this point is L0 mu 0, and as long as I'm inside this range, I need not actually start to look at how the latitude or longitude is changing over time. I can simply say my coordinate frame is fixed here, and from there, what is the location or the distance can be taken as a linear distance. So the curvature of the Earth is not really affecting it. So that's why I can consider this to be a flat space, and hence the name Flat Earth Navigation System. Everybody with me?
Yes, sir.
Yes.
All right. Let's proceed further. Okay, I'll also define, something got missed here. I think these pages got mixed up. This page should have come next. Yeah, this should have been page 3 here. 3 is coming after 4. So I'll cover this page and then I'll come back up. Okay. All right, so this NED frame, which we just talked about, we are going to represent it as N, frame of reference as N, and X, Y, and Z axis will be X superscript N, Y superscript N, Z superscript N. The origin ON here is defined as the location where the tangent plane touches the Earth's surface, reference ellipsoid. So you know that the Earth is not exactly spherical, and it's actually a more of an ellipsoid, and the World Geodetic System in 1984 formulated what is that ellipsoid's parameters, and that ellipsoid is now known as WGS 84. So whenever you want to convert a latitude and a longitude into a flat Earth space, whether it be in MATLAB or any of the known programs which do this, you will see that what is the reference ellipsoid based on which you want to do the conversion. And we typically choose the WGS 84 as the usual ellipsoid. However, there are different other models also that you can choose, but this is the most widely accepted model, and that is where we will follow this one for most of our cases as well. Okay, the location of this frame N relative to E, which was the Earth-centered Earth-fixed coordinate frame, is determined using two angles, the longitude and the latitude. And I think I have it opposite here. L is the longitude and mu is the latitude. Okay. And this is the reference frame that we are commonly using in most of your courses that you see otherwise. Okay, now we will define what are called body fixed frames. So we'll first define what is called as a body frame, and what we will do here is we'll denote this frame by the letter B, and X, Y, and Z axis as XB, YB, and ZB. The origin of this body fixed frame, we typically try to choose it to be at a convenient point on the graph. We don't want to choose it at a point which might be varying over time or which might be changing over time. So choosing the center of gravity of the vessel is usually not a great idea. Although it simplifies your equations of motion, the center of gravity need not keep constant. When you are on an onward journey carrying cargo, the center of gravity may be at one place, but when you are on the return journey, where you're only using the ballast tanks, your center of gravity will be at a different location. And so therefore it's time varying in that sense, and is not a convenient point to find out every time you're loading the ship. So therefore it's always better to choose this origin at a convenient point on the vessel. Typically what we will do is we'll choose this as the intersection of midship, waterline, and center line. Okay, so if I have a ship which is floating at some draft, I will look at where is the midship located, and at that location, at the center line, that is where I'll put my origin of OB. Okay. That is typically where we choose. And then we put our x-axis usually in the direction of the longitudinal direction of the ship. So along that will be the x-axis, and it is directed from the aft to the fore. And y-axis, we'll first discuss about the z-axis. Z-axis is pointed from the top to the bottom. Okay, so x-axis is aft to the forward, y-axis is top to bottom. So obviously, where should be y-axis?
Starboard.
Starboard side should be the y-axis. So it should be directed to the starboard side. All right. Now, with respect to this, what you call body frame, we need to also define something called as the flow frame. Now, this flow frame is not so important, but it comes in handy at some times when we are trying to compute the hydrodynamic forces on the vessel. So for that purpose, we will define what is called as this flow frame. And what this does is, all it is doing is, it aligns the x-axis with the craft's velocity vector. So let's say that this is my craft. Okay, but we know that when the craft is turning around and moving around, its velocity vector need not always be pointed in the longitudinal direction. And we saw this especially when we are looking at the craft is turning. You'll see that it will have some slip angle. Okay, so its velocity will be pointed some direction which is not exactly with the longitudinal direction of the ship. And that angle we'll define at a later point, which is usually called the side slip angle. But for now, what we will do is we'll define a flow frame with such that its x-axis is along the craft's velocity vector. Is that making sense?
Yes, sir.
Okay, so x is along that u, z is downward, and then therefore y should be towards this side. So this will be x flow, this will be y flow, and then z flow will be pointing downward. That's how it will look. And as the velocity keeps changing, so suppose as we are going through a maneuver, our flow frame will change. So therefore, at every time step, you actually need this flow frame to be computed in order to determine your hydrodynamic forces which are coming onto the body. So this flow frame is defined at every instant, and rather than a fixed flow frame which I have defined and doesn't change over time. It actually does change over time. Now, flow to the body transformation is characterized by angle of attack. So what angle at which the ocean currents, let's say, are attacking at the ship, and what is the slip angle, side slip angle, beta. So these two quantities determine how the flow coordinate system is oriented with respect to the body coordinate system. Now, don't worry too much about it. We are going to cover exactly how the two are related and what these exact angles are in a later lecture. We are going to come back to this when we talk about how to transform from one coordinate system to the other. At that time, we will discuss this in more detail. For now, just understand that there is something called a flow frame, which we will define so that we can determine what are the drag and the lift components which are acting on the body due to the flow around the body. This is primarily used for that lift and drag forces, and also it is sometimes useful when we are looking at line of control, path following control systems. So that's where also sometimes you may see this concept being used where the flow frame can come into the picture. But in general, the flow frame will not come into the picture very often, other than the fact that we want to capture the lift and the drag forces. Okay, so that defines all the different frames that we talked about. So what are the different reference frames we talked about? Can anybody give me the countdown of them?
Sir, Earth-centered inertial frame and Earth-centered Earth-fixed frame, NED frame, NED frame,
NED frame,
body frame and flow frame.
body frame and flow frame. Very good. All right. Let's continue now. All right. So now that we have defined these different frames of references, we'll define certain reference points in these frames. The most important is the origin OB of the body fixed frame B, and we'll represent that as coordinate origin, or CO. That represents where is the origin of the body fixed frame. And you'll see that this will play a significant role because we'll define most of the body fixed quantities with respect to this point. So this point is pretty important for us. The next one which we define is the center of gravity of the craft, and that is located at a distance xg, yg and zg away from the CO, or the origin of the body fixed frame. Okay. This distance xg, yg and zg, when expressed in the body fixed frame, is denoted by this vector rbg superscript b. So wherever I'm seeing a superscript, it is in that frame of reference that the vector is expressed in, and b to g is what I am trying to find the distance. Is the convention making sense?
Yes, sir.
Okay, so
Yes,
this vector is pointed from the B frame to the G point, and I am expressing that vector in the B frame. And that is what is given by xg, yg and zg. Similarly, the center of buoyancy of the craft is located at RBB, where I'm talking about where is the body. So here there is a little bit of a confusion as to what this B stands for, but just think of this B as the center of buoyancy. Okay, so where is the center of buoyancy in the body fixed frame from the body fixed origin? I'm trying to determine that, and that vector is expressed in the body frame. So xb, yb and zb denotes the coordinates of the center of buoyancy expressed in body fixed frame. All right, so now I'll come down. Yeah, this mismatch of pages is there. I'm going to correct it at a later point. I think I unknowingly scanned one in place of the other. Okay, the next reference point which we are interested in is the center of flotation. And this is nothing but if I take the water plane area of the craft, so if I see where the ship is floating, that is the water plane. Okay, so that water plane has an area of AWP, and where is that water plane's centroid located? That is what tells me where is the center of flotation. So let's say that this is the point which is the centroid, then this becomes center of flotation. Now I want to find out where that center of flotation is relative to the coordinate origin, and that distance is given as xf, yf and zf. So again, as per our convention, we denote this vector as rbf, so from the body fixed origin to the center of flotation, expressed in body frame. Okay, so notice that CO, which is the coordinate origin, has a constant location. As I said, this does not change with time. Whereas depending on the loading conditions, depending on what the ballast tanks levels are, how the weather conditions are, and what the motions the craft is experiencing, the location of CG, CB, and CF can vary with time. Okay. Now let me ask you this. As the weather conditions change, can CG change with time?
No.
No.
No, right.
It cannot change with time, right? Based on the weather, it cannot change. But with time, as time is progressing over a voyage, can the CG level change?
Yes.
Why?
Yeah.
Why can it change?
Fuel consumption.
Correct. Because of the fuel consumption. Because we are using up the fuel, so some of the mass is gone from there, so therefore the location of CG can be subject to change over time. Now, due to the weather,
Like maybe sir had internet problem.
Yeah, probably.
Should we message?
येस
Mm,
करतो का मेसेज तू
काय टाकू?
okay, am I back?
येस सर
Okay, looks like I inadvertently did something which I was not supposed to do, and I got logged out of the system. All right. Okay, I was asking the question that with weather conditions, can the center of buoyancy change?
Yes, sir.
येस
How can it change?
The sea surface levels are changing.
Correct. So the sea surface may be different at a particular time instant. I might see that.
अंडर वाटर वॉल्यूम विल बी डिफरेंट
Correct. So the wave might look something like this. So the underwater volume might be different. So the center of buoyancy's location may change over time. Right. Similarly, the center of flotation also might change over time depending on the weather conditions. So due to these different factors, that is why it is advisable to choose this coordinate origin at a location such that this is fixed and does not change with time. All right. Okay, now that we have defined the reference frames and the reference points, let's start discussing a little bit about the generalized coordinates. Now, when you hear the term generalized coordinates, what that means is that we are talking about variables that describe the configuration of the craft relative to some reference configuration. So with some reference configuration, what is the new configuration? That is what we want to define. And in general, for a marine craft, we will define the generalized position by a vector named eta, and that would be defined as xn, yn, zn, phi, theta, and psi. So xn, yn, and zn are the positions in NED frame. If you remember, NED frame is what we denoted by N, and Xn, Yn, and Zn are the location of the craft in the NED frame, and phi, theta, and psi denote the roll, pitch, and yaw angles of the craft. So not only is the craft translated by some distance xn, yn, and zn, but its orientation is also twisted by roll, pitch, and yaw. And here it is important to understand that the finite rotations are not commutative in nature. Okay, is everybody understanding what I mean by that? Finite rotations are not commutative in nature. Is that making sense? What do I mean by that?
A into B is not B into A.
Sorry, come again, Mala.
Like a rotation, say you rotate first with one angle and then with other angle. It's not the same as the other angle and then the first angle.
Correct. So if I interchange the order of rotation of two angles, then I need not necessarily end up in the same place. And that's what it means. And let's kind of see an example of it. And I think I've seen some of the undergraduates have seen this example before, but for the graduate students. So let's say I have a ship which is looked like this. Okay, x-axis pointed towards the fore, y-axis pointed towards the starboard, and z-axis pointed downward. Okay, and we are going to apply two rotations: one rotation over x, one rotation over z. So in one case, we'll apply the z rotation first and followed by an x rotation, and in the second case, we'll apply the x rotation first followed by the z rotation. Okay. In both cases, we'll start off from this position where the bow is facing you guys. Okay. Now, the moment I apply a rotation about the z direction by 90 degrees, the ship turns like this. Everybody with me so far?
Yes,
Yes,
sir.
sir.
Okay. Now the x was directed that way, y is directed towards me, and the z is directed bottom down. Right? So if I now apply a rotation about the x-axis, how will it rotate? It will rotate like this.
Yes, sir.
Yes.
Okay, so now in this final configuration, the keel of the plate or keel of the ship is facing you. Good way to remember it, right?
Yeah.
Now let's start back from the original position. Now we'll apply the order of rotation differently. We'll apply the rotation about x first. That will become this. Everybody with me?
Yes.
Now
Yes, sir.
about the z, the rotation will become this. Correct?
Right. Yeah.
Because the z-axis is pointing down on the ship, right? So when I rotate it, it should become, this should be the new position. Everybody with me?
Yes, sir.
Yes, sir.
Okay, so you can see that the two same rotations, one about the x-axis and one about the z-axis, as I change the order, my actual position of the ship is different, isn't it? In one case, when I applied the rotation about z first and then followed by x, this was the position. Whereas when I applied the rotation with x first and z next, this is the position. So finite rotations, where the rotations are of large angles, they are not commutative in nature. So the order of the rotation does matter. So therefore, when we define our rotation angles, we also have to define necessarily an order of rotation in which we will consider those rotations. Because if I interchange the orders, my new position will be completely different. So what Anand might tell me as roll, pitch and yaw will not match with my roll, pitch and yaw if we are both looking at different orders of angles. So that is very important when we are looking at these applications. Okay, let me come back here now.
So like for the if the rotation angles are small in two different axes, then do we consider them same then?
If they are really small, if the angles are really small, then yes, it is commutative. That it really doesn't matter which one I apply first because the angles are relatively small. And we'll see that once we derive the full rotation matrix, when small angle approximation we make, what do we get out of it? When we see that, you will be able to appreciate why they are commutative in nature. Okay, so the rotation matrix becomes commutative in the fact that whether I use one or the other, there is no nonlinear terms present, so therefore it becomes commutative. We'll see that. It's going to come up in just a couple of minutes, either today or tomorrow. Okay, let's go further. Okay, the generalized velocity of the craft can be defined by taking a derivative of the generalized position. So that is what a time derivative is denoted by this dot above. So eta dot becomes x dot n, y dot n, z dot n, phi dot, theta dot, and psi dot. Notice that eta and eta dot, both these vectors, generalized position and generalized velocity, are expressed in the n frame. You already see that with the position coordinates that they are in the n frame. Please remember that these Euler angles are also somewhat defined in the n frame. This might feel a little confusing, but they are actually angles which are defined in the inertial frame. So they are defined in the n frame. Now, we got the velocities in the n frame as eta dot, but typically we would like to find out what are the velocities in the body fixed frame B. So we want to know what is the velocity in the body frame, and that velocity in the body frame is denoted by a vector V, which we has components u, v, w, p, q, and r. And these here represent the translational, first three represents the translational velocity expressed in body frame B, and the last three represent the rotational or the angular velocity expressed in body fixed frame. So this is angular velocity and this is translational velocity. Okay, is that clear for everyone? The definitions, we will look at how these two are related in just a minute. We have not talked about the relationship between V and eta dot, and they are related through what is called a rotation matrix. But for now, the definition is that U, V, and W denote the translational velocities in the surge, sway, and yaw. The rotational velocities P, Q, and R represent the roll, your pitch, and your angular velocities. Yeah.
Can you just again show the representation of eta dot, the terms in eta dot vector? Okay, yeah.
Yeah, eta dot is nothing but whatever was.
Yeah, just, okay, fine, yeah.
Whatever is there in eta, we just take a derivative of it.
Okay, fine, yeah.
All right. Now, before we proceed further, we want to kind of define some notations so as to be consistent throughout our text, because we are going to have a lot of coordinate transformations. We are going to be talking more about this, and we don't have to, we need to keep a consistent notation in place. So for that, what we will do, we will use these two notations here. One is the vector notation, where we call a vector A as A1n times n1, A2n times n2 plus A3n times n3, where n1, n2, and n3 are the unit vectors that define the coordinate frame n. Okay?
Yes.
And the extent of that vector along the n1 direction is A1n. Extent of the vector A in the n2 direction is an2. The extent of the a vector A in n3 direction is an3. So if I take A dot n1, I'll get back this value A1n. If I take A dot n2, I'll get A2n. Because whenever I take a dot product with any of these two, n1 dot n2 or n2 dot n3, they'll all be zeros, because these are in three orthogonal directions. Is that making sense?
Yes, sir.
Okay. Now, the same vector may also be expressed in a coordinate form. that vector A, I may also write it as a vector An, where I am denoting that this is denoted in frame of reference n. Okay, this tells me that expressed in n frame. And then I simply write it as a vector of three real numbers, a1n, a2n, and a3n. And we'll kind of interchange between these notations as needed, because sometimes we'll need to take cross products, sometimes we'll try to express those cross products as matrix multiplications. So it's kind of easier for us to switch between these two frames or between these two notations, but please understand that they have the exact same information in them. There is no extra information in one form compared to the other. Is everybody with me?
Yes.
Okay, fantastic. All right. Now, armed with these notations and the reference frames and the coordinate points that we have defined, we will now define a certain vectors and what they mean. We'll denote the position of the coordinate origin relative to OE as PEB, and when we express this vector in the E frame, we'll denote that as PEB superscript E. Tell me if you are able to understand this notation. It's a vector directed from E to B expressed in E frame. Yes, no?
Sir, E was Earth fixed frame, right? ECEF, right?
Correct. ECEF. So it
Okay.
means this OE here is center of Earth.
Yeah. Okay.
Okay, and this CO is the coordinate origin of the body fixed frame or OB. So I'm directing a vector from OE to OB. I'm going from E to B, but I'm expressing that vector in the E frame.
Okay.
Okay, so based on that notation, without looking at the text next to it, can you tell me what this will be? PNNB?
Position of OB is represented in the NED frame.
Correct.
Position of NED frame to body.
And it is expressed in NED frame.
Yeah.
The vector is expressed in NED frame. That is why you have the superscript n. Now, in a similar way, we define the velocity also. So VNB E represents the linear velocity of the coordinate origin. Okay, so we are looking at what is the velocity of the coordinate origin expressed in the E frame relative to the point ON. So we want to find what is the relative velocity of CO with respect to point ON. But that vector, we are expressing it in E frame. Is everybody following me?
Yes, sir. Yeah.
Sir, what about the B, sir?
What about the B?
That NB, that is
Ah,
body
so
frame.
yeah, that B is that CO, no? That CO is nothing but OB, right?
OB.
Yes, sir.
This is the origin of the body fixed frame. So we are going from ON to OB, and I'm trying to express that vector in E frame.
Yes, sir.
Okay. Similarly, VNB, this one, VNNB, will be the linear velocity of the OB point relative to ON point expressed in N frame. Okay, notice that these two vectors are the same vectors actually. Only difference is one is expressed in the E frame, the other is expressed in the N frame. So if I took a magnitude of both these vectors, those two vectors should be the same exactly. Is everyone with me so far?
Only the directions are different, right? Because of the representation, change in the representation of the reference frames.
The direction is still the same. It's the same vector.
Okay, like with respect to the reference frame, the vector is different, right?
Correct.
In reality, like in a common global frame, both of the vectors are the same. But like with respect to the corresponding reference frames, the vector appears different.
Correct. So the idea is that the vector is the same, but its what you call XYZ components along different frames is different.
Yeah.
So a simplest example, if you want to really look at it, might be drawn like this. Let's say that I have this vector and I have one coordinate frame which is looking like this, which are orthogonal like this. So this is X and this is Y, let's say. And the other frame is, let's say, at an angle. Now, if I drop the perpendiculars, then this will be, let's say, x1 and this will be y1. Okay, and these frames will be, let it call x2 and y2. So when I drop the perpendiculars on these frames, this one will be x2 and this one will be y2. So even though x1 and x2 are not same, y1 and y2 are not same, the vector is still the same, no matter where the reference frame looks like.
Yes, sir.
Is that clear for everyone?
Yes, sir.
Anand?
Sir, can you come again, sir? Last point.
Sure. See, let's say that I have defined one frame here. I'll call this frame 1. Okay, x1, this is y1, this is x2, and this is y2. Okay. Now I'm taking the same vector, which is represented by this arrow here. Okay.
Yes, sir.
And I'm dropping what are the components of the vector in each frame I'm looking at. So if I'm looking at the x1, y1 frame, these two frames, okay, so I drop a perpendicular here, that will be x1. I drop a perpendicular into y1 axis, that will be y1. So in this coordinate frame, if I want to locate where that point is, vector is pointing to, I will say x1 times e1 plus y1 times e2. This will be the vector representation of it, isn't it?
Yes, sir.
But whereas if I took it to the other frame, which is nothing but it is rotated by some angle between the two of them, right? Now let us say that in that other frame, I want to find out what is the x and y components. I can see that when I drop a perpendicular on the x2 axis, that value is x2. So that will be x2 times, I should call this something else. Wait a minute. Yeah. E11, E12. This should be E21 plus Y2 times E22. Right? So Y2 will be the component along the Y2 axis and X2 will be the component along the X2 axis. So the vector representation will be given by this. Is that making sense, Anand?
Yes, sir.
Here what I am saying is E11 is going across in the direction of x1, unit vector in this direction. E12 is the unit vector in this direction. The unit vector along this direction is E21 and the unit vector along this direction is E22. Is
Yes,
that
sir.
making sense? So I can write the same vector in this representation when I am expressing it in the coordinate frame x1, x2, y2. And I can write it in this representation when I am writing it in x1, y1 frame. Got it?
Yes, sir.
But the vector is the same. Only its components has changed, but the vector itself has not changed. It still looks like the same vector, right? That is the idea. Clear or still not clear?
So the direction of the vector with respect to frame is changed. That's it.
Yeah, the vector stays the same, but its direction with respect to the frame has changed. You have put it very succinctly, precisely. Okay, that's all that has changed. All right. Okay, now we also define the angular velocity in the same manner. So omega nb b represents the angular velocity of the body fixed frame with respect to the n frame expressed in body fixed frame. Okay, is that making sense now based on whatever we have seen so far?
Yes, sir.
Okay, all right. In a similar manner, we will define the force and the moment as well. So a force vector F and B represents the force with a line of action passing through the origin point OB expressed in N. So this is expressed in N and it is talking about what is the force acting at the origin point OB. Everybody? Only difference here is that you don't see two coordinates here because this is not a position. It is talking about a force. So force just has only a single point of application, and that point of application is what we are denoting here.
Yes.
Everybody?
Yes, sir.
Yes, sir.
Okay. Okay, similarly, moment is denoted as MNB, represents the moment about the O point or about the O frame, the B frame, expressed in N frame. The vector is expressed in N frame. Is that making sense?
Yes.
Okay. Now, coming to the Euler angles, we will define the Euler angles as capital theta here, the convention, and B. Again, what is the Euler angles? Which will help me to go from N frame to B frame. This convention of why it is going to be going from N frame to B frame will be a little bit clear when we start talking about the rotation matrices. But hopefully, now you know that this is nothing but a vector of phi, theta, and psi. That's all it is. Okay. Now, in a similar manner, rather than Euler angles, we can also define the orientation using Quaternions. And if we define the Quaternions in terms of that, then it would be defined as Q and B would be defined as the unit quaternion from B to N. But for our purpose, we will not focus more on Quaternions. We will not cover that in detail. We will stick to Euler angles because for most ship dynamic positioning, DP applications, Euler angles are sufficient. Okay, these are sufficient. The Euler angles are insufficient in some cases, and we'll talk about where it is insufficient, but those cases really don't occur when we are looking at ship dynamic positioning problems. So we'll not bother ourselves much with that aspect. Okay?
So like in the notation for the Euler angles, both are in the subscript, and for Quaternions, n is in superscript and
Correct, because quaternion is actually a vector and you have a reference frame in which you have to express it. Whereas Euler angles do not have anything of that sort. So which is why the reference frame is given as theta and b, because we are planning to go from n frame to b frame. Right? So in retrospect, when I told you that Euler angles are kind of a little dicey in the sense that they are not defined in any particular reference frame, that is why you're not seeing anything up here. Not seeing anything up here.
Yes.
Right? Because they define the angles and the orders which will allow me to go from n frame to b frame. Whereas a quaternion is a different issue altogether, because it is defined in a certain particular frame, because it will have four components: q0 plus q1 times e1 plus q2 times e2 plus q3 times e3. And what it is doing is it is kind of defining that the rotation is defined about an axis about which the rotation is happening. So unlike the three rotations which we are saying that they will happen in orthogonal directions, quaternion doesn't define the rotation in that manner. Quaternion kind of in a qualitative sense tells me the direction of the axis about which the combined rotation is happening, and q0 denotes in some sense what is the angle by which it is rotating.
So like for the Euler angles, we are defining the say ZYZ or one of the possible three transformation. Like
Correct, but for a quaternion there is no such ambiguity.
So there will be one vector, and about its axis it will rotate.
So we define a vector about which the rotation is happening, and about that vector we just rotate by a certain angle. Okay. Only difference is here that that q0 is not the actual rotation in quaternion. That comes in axis angle representation. Here q0 represents cosine of theta by 2, where the rotation is by angle theta. Okay, and this unit, this q1, q2, and q3 represents a vector whose magnitude will be sine of theta by 2. So that when I square and apply them all, when I take q0 square plus q1 square plus q2 square plus q3 square, I get 1. Okay, that is why it's called unit quaternions. But don't worry yourself too much with it. We will come back to this if really time permits, but for now I'm not planning to cover quaternions in too much depth. But yeah, if time permits, we'll come back and try to see, especially with respect to Ross, how the quaternions are being used. Okay. All right. With that said, that will be all for today. We'll stop right now.
Sir,
Yes, go ahead.
in the maneuvering course, we studied about only two frames: the global frame and the body fixed frame.
Correct.
And here we are talking about 5 frames, rather 4, if we discard that flow frame.
Yes,
So,
right. 4 frames, right.
So the global in maneuvering course is NED in this particular course.
Correct.
NED, yeah, okay, yeah, that's
Correct.
what that
And
was
the body frame is the body frame.
Yes, okay.
Okay. Only the two new things which are what you introduced are the Earth-centered frames, Earth-centered inertial and Earth-centered fixed.
Yes.
Those are introduced so that we can understand how a latitude longitude can be converted into a flat Earth frame. That will be important, especially when we are looking at GPS applications. So when GPS gives us a latitude and a longitude, how do I convert it and get actually where the location of the vehicle is? That is what we are going to cover in this course as well. So for that, we have introduced those extra frames.
Yes.
Okay. Any other questions? Okay. So in that case, let me stop recording.